Hi students, now problem number 3 in atomic and nuclear physics. So subdivision A, a hydrogen atom is excited by radiation of wavelength 97.5 nanometer. Find the principal quantum number of the excited state. B, show that the total number of lines in the emission spectrum is n into n minus 1 by 2. Compute the total number of possible lines in the emission spectrum. It's a very interesting numerical problem. So the first part we will solve first. It is given that the lambda value is 97.5 into 10 power minus 9 meter. So what is the corresponding energy? We will find out. So the corresponding energy E is equal to hc by lambda. So h is the Planck's constant, that is 6.626 into 10 to the power of minus 34 joule second. C is the velocity of light, that is 3 into 10 to the power of 8 meters per second, divided by 97.5 into 10 to the power of minus 9 meter. Okay, and the unit is now joule. Now I can also express this energy in electron volt by dividing this value by the charge of the electron. So E is also now equal to 6.626 into 10 to the power of minus 34 into 3 into 10 to the power of 8 divided by 97.5 into 10 power minus 9 multiplied by 1.6 into 10 to the power of minus 19. Now the unit has changed to electron volt. Now let us find the values. The product first, the numerator is 6.626 multiplied by 3 is equal to 19.878 divided by denominator product is 97.5 multiplied by 1.6. So 1.6 that is equal to 156. So multiplied by 10 power minus 34 again multiplied by here minus 19, here power is minus 9, so that it is minus 28. Minus 28 when it comes up it will become plus 28. Plus 28 added with 8 will become plus 36. So this will become 10 power 36. So now it is 19.878 divided by 156. So that is equal to 0.1274 into here 10 power 36 minus 34 is 100 electron volt. Therefore, this energy is equal to what? 12.74 electron volt. So this is the energy supplied by the photon on the hydrogen atom. By taking this energy to which energy state the hydrogen atom will be shifted. Okay. So this energy also can be taken as En minus E0. Okay, this is En minus E0. So I can take that this energy is delta E, that is equal to 12.74 electron volt. But this delta E is also equal to 13.6 into 1 minus 1 by n square. In the normal formula, it is 13.6 into 1 by n square minus 1 by m square, okay, where m is the higher energy state, n is the lower energy state. Here actually m is replaced by n and n is replaced by 1, that is ground state. Therefore, this energy is also equal to ground state energy 13.6 into 1 minus 1 by n square, okay. So this is now equal to 12.74. So this is equal to 12.74. So now we need 1 by, there is 1 minus 1 by n square. So I will write 1 minus 1 by n square is equal to 12.74 divided by 13.6. So this we have to find 12.74 divided by 13.6, that is equal to 0.9367. Okay, what next? I will take this minus 1 by n square to the other side. So that 1 by n square is equal to 1 minus 0.9367. So 1 minus 0.9367. So this is equal to 0.0633. 0.0633 is coming. I want to find the value of the principal quantum number n. So we have got the value of 1 by n square. So taking reciprocal now, n square is equal to 1 divided by 0.0633. Okay, so the reciprocal 1 divided by 0.0633. So this is equal to 15.79. Therefore, n is equal to square root of 15.79. Now, roughly speaking, square root of 16 is 4, is it not? What is the square of 3 is 9. Square of 4 is 16. So this is very close to 16. Therefore, we can take nearly equal to 4 itself. Okay. Therefore, n is equal to 4. So what is the value of the principal quantum number after taking this energy of 97.5 nanometer? The hydrogen atom is shifted to n is equal to 4th state. Is it not? N is equal to 4th. Therefore, now subdivision B, the number of possible transitions, what is given? The total number of lines. So n is equal to 4 means, you see here, this is n is equal to 4, then n is equal to 3, n is equal to 2, and finally n is equal to 1. So like this, the energy level diagram you draw now. So when the hydrogen atom is shifted, it is absorbing the photon and shifted to n is equal to 4, and it can remain only for 10 power minus 8 second in the higher energy state. Afterwards, it has to return to the ground state. What are all the maximum transitions? It can directly come from n is equal to 4 to n is equal to 1, or it may come from n is equal to 4 to 3, then 3 to 1, or it may come from n is equal to 3, then n is equal to 2, and from there also it may come back to n is equal to 1. Now, direct transition from 4 to 1, this is one possibility. Then 4 to 3, 3 to 1, here two possibilities. Okay, and 4 to 3, 3 to 2, then 3 to 1, here is how much? 3 possibilities. So what are the maximum number of lines available during these possible transitions is 1 plus 2 plus 3 is equal to what? Total 6. So total 6 possible transitions. So here compute the total number of possible lines using the above formula. So when n is equal to 4, the total number of transitions, okay? So total number of lines emitted, okay? Total number of lines emitted is equal to n into n minus 1 divided by 2. So this is 4 into 4 minus 1 divided by 2. So 4 by 2 is 2. 4 minus 1 is 3. So this is equal to 6. Also from the energy level diagram, we have proved that there are 6 possible transitions. Okay. So there are 2 sections. In the first section, if the wavelength is given means first you must convert or find out the energy in terms of joule as well as electron volt. Then we have to find out the principal quantum number by using the expression 13.6 into 1 minus 1 by n square. Okay, and after finding the value of n, that number of lines emitted is given by n into n minus 1 divided by 2. This is not explained anywhere in the theory of your textbook. Directly in the numerical problem they have given. So it's an added information required for solving the numerical problems in the competitive exams like NEET and JEE. I hope you must have understood well. Fine.